Okay, so I'm going to go through quickly. This will be the second video, second part. Going through the questions, and I'm going to try to get up through 39. What piece of lab equipment would you use to measure mass? For this, what we use is a balance. We use an electronic balance in class. And we measure mass in grams. What piece of lab equipment would you use to measure volume? What units would this measure in? Typically, we think of, like with liquids, we would use a graduated cylinder. This is also used for the irregularly shaped solids. That's the technique called displacement. Other than that, you could technically say a ruler for regularly shaped objects, because we can do length times width times height. All right. If we're going to use the graduated cylinder for anything, then we're going to have units called milliliters. And of course, if we do the length times width times height, we typically measure those in centimeters. That would come out to be centimeters cubed or cubic centimeters. Temperature, we're going to use a thermometer, and those could measure in different units. Typically in science, we will see them in degrees Celsius. What tool could be used to measure pressure? It could be, we could use a manometer, or most commonly a barometer. And what this would do is, in the early days, push mercury up the tube, and we can measure how high, like, atmospheric pressure pushes that mercury up the tube. Originally, they found that it went up, the mercury went up the tube 76 centimeters, or 760 millimeters. And since it's millimeters of mercury and the symbol for mercury is Hg, that's a typical unit that we have for millimeters of mercury. So that was 760 millimeters of mercury. And then they said, let's just make this a unit called the atmosphere, 1 atmosphere. We could also use units like kPa, or maybe even PSI. Some various units we see there. All right, and number 5. So on number 5, we could use that density triangle that we had before. I need to make it larger than that. But this is the density triangle. Looks like this. And basically the way you use it is whatever you're looking for. For example, in A, we're looking for density. So just cover that one up. If you cover that one up, you're left with mass over volume. So mass divided by volume. So in this case, we would have 42.751 grams over 22.61 milliliters. And when you divide that, the number you should get is something like 1.89. I didn't do significant figures, but that would be your answer to A. I'm just going to erase that. And paying attention to our units, it's grams divided by milliliters, which gives us grams per milliliter. So that unit on the bottom, the volume unit, can change depending on what you're using. As you see in B, we have cubic centimeters that are being used. So in this problem, we are looking for mass. So if I cross out mass, I now have density next to volume, which implies density times volume. So that would be 2.1 times 23.10 cubic centimeters. And so there my units, or my answer is going to be 48.51. and my units are going to be grams. And then the last one, C, just same thing as A. We're going to take this mass of 123.622 and divide by 35.95, and we should get an answer that is approximately 3.44. Again, our units are going to be grams divided by milliliters. All right, room temperature density is a property of a substance. So we can actually identify substances based on their density. Density can change, of course, with temperature. We increase the temperature of something, the particles will move faster and spread out, which would affect their density. Number 7. What's wrong with the following model? Well, we start this reaction. We have 2 copper atoms and we have 2 oxygen atoms. And when we combine them, they can rearrange and combine differently, like a copper attached to an oxygen, that's fine. But if we had 2 coppers to start and 2 oxygens to start, that's what we should have at the end. However, we have an extra set. We cannot have that. This is law of conservation of matter, of course. Matter cannot be created or nor destroyed. Matter, geez. And in this model, it's implying that matter just appeared from nowhere. It was created. That can't happen. Okay, number 8. If you dissolve 25 grams of Kool-Aid mix into 150 grams of water, all you're doing is you're adding the Kool-Aid mix to the water. All you got to do is just add them together. Nothing's happening. Nothing's going to leave the system or anything like that. So we're just going to end up with 175 grams total. A piece of wood has a mass of 10 grams. What would happen to the mass of the wood if you light it on fire? Why would this happen? Now, when you burn something, that's combustion. And oxygen would actually, if this is the system, oxygen would actually enter the system, which would add mass. However, we are also going to be losing matter as well. So overall, if we burn this piece of wood, I would expect the mass to decrease. Okay. Okay, the matter would be leaving the system. More likely, more matter would be leaving than entering. Okay. Number 10, what happens to the mass of water after it's been boiled for 25 minutes? It should decrease. And the reason why is because we're going to be losing water to the air. It's becoming a gas. What is the gas above the boiling water made of? That would be the water still. We call it water vapor because it's now in the vapor phase or gas phase. 12, sometimes a closed can of Coca-Cola that is cold will sweat. What's the liquid on the outside of the can? How does it get there? That's just going to be water. So in the air, we have water. It's called humidity. There is water vapor in the air all the time. If we have a cold can, when the water vapor in the air cools, it will actually form back into a liquid on the can. Can matter be destroyed? No. Explain. Well, law of conservation of matter again. Matter can leave a system. So we can see matter be lost, we can see mass decrease, but we can't just destroy it. All right, 14, explain the difference between a solid, liquid, and gas. Draw a particle diagram. So in a solid, we're going to have particles that are close together. According to the kinetic molecular theory, particles are moving, even in solids. They do not rearrange. They don't move around relative to one another. We just use these little motion lines that look like quotes, and just to show that the particles are moving back and forth. Now, if we add energy, we can turn this solid into a liquid, which means the particles are going to spread out a little bit. And they are going to move around each other, so we're going to draw arrows, just short little arrows, random directions. So the particles become a little more spread out. Now they're moving around. And if we get to the gas phase, particles are now going to go everywhere. We'll draw bigger arrows to show that they are moving faster. They have more energy. All right, we also talked about like solids, since they do not move around. Those would have definite shape and volume, regardless of the container you put them in. Liquids have definite volume. The size, the amount of space they take up is not going to change, but the shape can change depending on the container, and the gases, shape and volume will change with the container. They're the same as the container. 15, what substance will have particles with the strongest attractive forces? So solids with the particles closest together will have the strongest forces between them. Gases would have the weakest. Liquids right in the middle. How is this proven in your diagram above? We can see the particles more spread out in the different diagrams, showing that there are more attractive forces where they're close together, and if they're more spread out, they're going to have less attractive forces. Okay, provide examples of ways that particles can change movement, of course, with temperature. So if temperature increases, particles are going to move faster. They'll also spread out when we add energy. And 17, what causes pressure? Pressure is all due to particles colliding with the sides of a container. Particles will collide with each other, but what we actually see as pressure is particles. Having some mic issues. Um, what does temperature measure? So the speed of the particles, really, which we call the average kinetic energy. Term to remember. That's the speed of the particles. That's really what temperature is showing. These particles are moving faster. As a result, more collisions are spreading out and bringing the liquid inside to a higher level, which gives us a higher temperature reading. What is a Kelvin scale? It's a scale that's based to align with kinetic molecular theory and the ideas of energy. How does it relate to the Celsius scale? If we take Celsius and add 273 or 273.15, if you want to be a little more accurate, that would give us a Kelvin temperature. That's not in degrees, just Kelvin. And the idea with this too, we would also see on this scale absolute zero. And so that would be theoretically where particles stop moving altogether. So the more movement we have with the particles, the more kinetic energy, the higher the reading is going to be on the Kelvin scale. There are no negative temperatures on the Kelvin scale. that would imply that there is negative energy or negative movement, which we can't have because it would still just be movement. Number 21, how does a straw work? And this is going to work because of atmospheric pressure or pressure differences. Okay, so we have the pressure on the outside that's pushing down will be greater than the pressure in our mouth, which is going to cause the liquid to move up the straw. What factors affect the pressure of a gas? So if we look at the other variables, we looked at the volume. Like if we decrease the volume, we're going to increase the pressure. If we change the temperature, so if we increase the temperature, that's going to cause a gas to have more pressure as long as it's in a non-flexible container. And of course, N, which stands for the amount of gas. If we added more gas to a container, it's going to increase the pressure. Okay. For solids, typically we'll see those in cubic centimeters, units for volume. A liquid, we're probably going to have milliliters, and for a gas, a lot of times we'll see those in liters. How is atmospheric pressure related to altitude? It is inversely proportional. So if one goes up, the other goes down. The higher the altitude, then the less air you're going to have. And if you have less air, you're going to have less collisions, which means less pressure. So higher altitude, less pressure. Okay. So on 25, these problems, what I do on these, we have to use our conversions that I gave you earlier. But I always start with what's given. They tell me there's 3,000 millimeters of mercury. Okay. And what I'm going to do is I'm just going to multiply that by a conversion factor. This is how I do it. Other teachers might do it differently. But whatever unit is here, I'm going to put that on the bottom of the conversion factor. And then whatever unit I'm trying to find, I'll put that on top. And those conversions earlier that I showed you, you should see that 101 right there. You should see that 101.3 kPa is equivalent to 760 millimeters of mercury. So that's what I want to use here. So that's what I'm going to put in. The kPa, I'm going to put 101.3, and for millimeters of mercury, 760. So I would just multiply 3,000 times 101.3 for a top answer. Use 760 on the bottom. The top answer, I just calculated it all together, but it should come out to be approximately 400 kPa for an answer. So same thing here. What are you starting with? 87.9 atmospheres. Multiply by a conversion factor. I'm going to put ATMs on the bottom, and then what I'm trying to find on top, which is torr. And torr I didn't list earlier, but torr is really just another name for millimeters of mercury. So it's going to be 760 on top and 1 atmosphere on the bottom. So all you got to do here is 87.9 times 760 divided by 1, which is just going to be the top answer. And I get 66,804. All right, and the last one, 26.11 psi will be our start. So I'm going to put psi on the bottom. I'm going to put kPa on top because that's what I'm trying to find. In our conversions, again, we'll use that 101.3 kPa, and I'm going to use 14.7 for psi. And if I multiply that out, I'm going to get 26.11 times 101.3. It's going to be 2,644.943. Divided that by 14.7, and my answer comes out to be 180. Okay, make a graph that shows the relationship between pressure and volume. So it makes sense that if I have volume and pressure, if we increase the volume, we're going to allow more room for the particles to move. If there's more room for the particles to move, there will be less collisions with one another, and there will be less collisions at a lower rate with the sides of the container. So as the volume increases, the pressure should go down. We call this an inverse relationship. And the idea is it can't continue to go down always, because eventually it would say that there's no pressure, but as long as we have particles, there is pressure. So the more accurate graph is actually curved at the bottom. Okay, 27. So I'm just going to use that relationship where if I take degrees Celsius and add 273.15, with my students, I just said 273. I should maybe I'll do this. All right, so this is Kelvin. So if I just take 83 degrees Celsius and add 273.15, I am going to get 356.15. Now, in this one, I have Kelvin, so I need to actually subtract 273 to get Celsius, and so I'm going to get 27 degrees Celsius. All right, number 28. So on these, we use the IFE charts, IFE charts, whatever you want to call them. So we have initial conditions, we have final conditions, and we have the effect. And our variables that we use will be pressure and volume and temperature and amount of gas. So in this first one, it says we have 5 liters. Really what we need to know here is we have to make sure that we understand what these units are for. 5 liters, liters are units for volume. So I'm going to put that under volume for my initial condition, and it's at 1.08 atmospheres. Atmospheres are units for pressure, so that will go here. All right. And then it says what pressure. So they want me to find a new pressure or a final pressure. So I'm just going to put that question mark there under pressure, final. And it says the volume goes to 10 liters. This is 10. All right. And it says the temperature stays constant, so I can ignore that. It doesn't say anything about the amount of gas, so I'm going to ignore that too. And now if we look at the effect, so the volume from initial to final actually went up. So we got to know our relationships between pressure and volume and temperature. Pressure and volume is the only one that is inverse. The two temperature ones, anytime we have temperature involved, it's going to be direct. So temperature and volume are direct. Temperature and pressure are direct. So however you want to remember that, but you got to memorize that. Anytime temperature is involved, we have direct. Pressure and volume are an inverse relationship. What that means is if the volume increases like this, then the pressure should go down. All right, so I'm going to start with the thing that we're trying to find, the pressure. I'm going to just write 1.08 atmospheres. And then I'm going to multiply by a conversion factor, and the conversion factor is going to be the thing I know, which is volume. And I've got two options. I can either do 5 over 10, or I can flip it upside down and go 10 over 5. What I'm going to do here is I'm going to go 5 over 10. And the reason why I'm going to do that is because I want the smaller number on top. Why do I want the smaller number on top? Because I know that this 1.08 should decrease. So by putting the smaller number on top, it's going to make this go down. We can do the math to check. So I'll do 1.08 times 5. I get 5.4. I'll divide that by 10, and it comes out to be 0.54. And my units here are going to be atmospheres. I should put my units here. And that's your answer. So that makes sense. We did see the pressure go down. We're good to go. 29, so same thing. IFE chart. It tells me that the temperature is 25 degrees Celsius, but if I read through the problem, I see that the temperature stays constant. So really I can just ignore that in this problem. They're telling me the initial conditions are 3.60 liters and pressure of 1 atmosphere. So I have volume and pressure again. So let's do that same thing. That's all I'm going to be concerned with. The pressure originally is 1 atmosphere, and the volume is going to be 3.60 liters. It says what will be its volume so they want to find the final volume if the pressure goes to 2.50 atmospheres. So it goes up 2.5 times, okay? So if I compare the initial to the final, pressure goes up. Again, pressure and volume, it does not involve temperature, so this is an inverse relationship. That means if the pressure goes up, this volume should go down. So let's take that 3.60 liters and let's multiply it by a factor that makes it go down. That means that we got to put the smaller number on top again. So I'll put the 1 atmosphere on top, and I'll put the 2.50 atmospheres on the bottom. And so I'm going to get 3.60 times 1 is going to be 3.60. And divide that by 2.5, and I'm going to get 1.44 liters. Important thing, remember that when you do these problems, always make sure that your Celsius temperatures are changed to Kelvin. Just wanted to say that before we forget. We'll see that in number 32. All right, number 30, we have another volume and pressure problem. These all look like volume and pressure problems. So, same thing, we have a volume of 11.2 for initial. We have an initial pressure of 0.860 atmospheres. What is the new pressure if the volume becomes 15 liters? So the volume is increasing, the pressure should go down. So I'm going to do 0.860, and I'm trying to go faster, so I'm just going to write out the equation. So again, smaller number on top. Multiply the 0.860 times 11.2, and then divide that answer by 15. 31, we have a volume of 12 liters initially. We have a pressure of 1 atmosphere. Final says what if the pressure of gas is increased to 2 atmospheres, what is the new volume? Okay, again, the pressure goes up, volume should go down. So again, when I take that 12.0 liters, I'm going to multiply by a conversion factor that has a smaller number on top. And one thing to note here is that whenever these change by a certain factor, like you see here, pressure doubles, the other variable is going to change by the same factor. It's easier to see in direct relationships because, like, if something doubles, the other thing is going to double as well. In this case, because it's an inverse proportion, if this doubles, then this should go down by half. So your answer on this problem should be 6. All right, so at number 32, we actually get to use temperature. I'm just going to use the conversion of 273 to Kelvin. But we have 3.75 liters. That's a volume. And then it says it's heated from 30 degrees to 55. So my initial temperature, I've got to change this to Kelvin. So it's actually going to be 30 plus 273 or 273.15. That's going to give me 303 Kelvin. So I'm going to put that here for initial conditions. What would the new volume be? assuming the pressure has remained constant, so we are heating it to 55. So 55 plus 273, and that's going to be 328. All right, it's early. 328 Kelvin. So this problem involves temperature, so that means it's going to be a direct relationship. We can see the temperature is increasing. Since it is a direct relationship, the volume should also increase. So this time, when I take my 3.75 liters and multiply it by the temperature conversion factor, I'm going to actually want to have the larger number on top. And that's how you solve that. To do the actual math, 3.75 times 328 equals 1230. Divide that by 303, and I get 4.06. Did the volume go up? It did. Good. All right, if a gas is in a rigid container, that means the volume can't change. Initial pressure of 140 kPa at 20 degrees Celsius. So I have initial pressure of 140 kPa. Temperature of 20 degrees Celsius, which when I add Kelvin actually becomes 293 Kelvin. What should the pressure be? Question mark. If the container is cooled to 7, which would actually be 280 Kelvin. All right, so the temperature is going down. Again, anytime we have temperature involved, it's going to be a direct relationship. The pressure should also go down. So your equation should have the smaller number on top of the conversion factor. That would be 280 in this case. And there is your equation. All right, so 34, what is the freezing point of this substance? So what we have here in this diagram, we start off at the beginning, lowest temperature. That means leg A here, we're going to have a